In 2016, the ScanPyramid project discovered a large void in the Great Pyramid, somewhere above the Great Gallery. This generated interest around the world, tamed by the realization that there is no way for us to peek into this space. This video presents a feasible and minimally invasive way to do this in our lifetime. We'll first briefly cover the ScanPyramids project and Muography. Then we'll discuss the proposal. If you want to see more videos, please like and subscribe. ScanPyramids is a joint project between French and Japanese companies and universities with access to the Egyptian government. It operated in the Great Pyramid between 2016 and 2019. Its researchers detected two unknown empty spaces: a short corridor behind the chevrons on the north face, and a long void above the Grand Gallery. The 2023 physical confirmation of the north face corridor, predicted by the ScanPyramids project, validated the success of Muography. When people hear cosmic rays, some may imagine sci-fi weapons. But most cosmic rays are nothing more than just protons, aka hydrogen nuclei. But hydrogen is all around us, so why are cosmic rays considered dangerous? The problem with cosmic rays is that they travel at near light speed, with energy that can damage bodies and electronics. If you lived on Mars, you'd really have to worry. On Earth, our atmosphere and magnetic fields shield us. When cosmic rays hit our atmosphere, they break up into showers of lesser particles. About 2% are muons. While all muons will die within a split second, some will reach the surface and some will interact with matter. Like in this cloud chamber, though not all traces are muons. By the way, here's a mini shower, probably the result of hitting this building. And here are the fireworks you get with a radioactive source. Muons can pass through big objects like mines, volcanoes, nuclear plants, etc. To resolve details like pyramid voids, you need months of data. Then you need to analyze it to compute spatial directions. This takes time. Finally, you can compare the results with simulations to see any anomalies. ScanPyramids use three ways to collect data: nuclear film in smaller spaces, a large scintillator in the Queen's Chamber, and muon telescopes outside the pyramid. They all confirmed each other's findings. Soon after the void's discovery came proposals for accessing it via drilling. An Italian academic suggested drilling upward through the ceiling of the Grand Gallery. This is unlikely to happen, as it would mean drilling a hole some 30 to 50 feet long. Other downsides are listed here. Peter James, a British engineer who worked on restoring the step and bent pyramids, wants to drill to reach the new void. He wanted to drill into the bent pyramid, but the Egyptians wouldn't let him. He says it's because the Egyptians want to keep some mysteries, to keep the tourists coming. Maybe they didn't let him because he wanted to drill a hole 34 meters long and 10 centimeters wide. The ScanPyramids project also proposed drilling a hole, then injecting an inflatable mini blimp, equipped with cameras, into the void to explore it. They don't specify where to drill from. The distance given, 5 to 10 meters, suggests the relieving spaces above the king's chamber. This seems unlikely to be approved by the Egyptians, as the limestone here bears the heavy load redirected by the chevrons above the relieving chambers. It's already been weakened by Colonel Weiss's blowing up access shafts around it. The plan we'll propose aims to achieve the following goals: minimize drilling, damage, and impact on tourist traffic. The key idea is to access the void from within one of the pyramid's northern shafts using robots. In the first stage of the plan, we'll need to much more accurately delineate the void's position and shape with respect to the northern shafts, so we can find the shortest distance between them. This distance ranging can itself be done from within the shafts. It would be done with Muography, but using smaller, thinner, and lighter films that fit into the shafts. Such size reduction seems feasible. Kunihiro Morishima, the Muon film specialist on the ScanPyramids project, himself considered placing films there.
本当最初のピラミッドの計画立ってる時って女王のまだここ人入らないから置けるって話が最初にあって、で この中に検石入れれないかって話も実はしてたんですよね。原子核乾板だと小さくなるんで、この中入れちゃえるんですよ。
It means fitting muon films in the shafts is plausible, but it may require a custom size. Here's how it could be done. We'll use a robot to deposit the muon films in the northern shafts. First, the robot will go to the furthest desired placement spot. Then, while backing out, the robot deposits a film. The film may have metal points for feet and spring-loaded folding-out arms to keep its position. In the Queen's shaft, the films will be placed horizontally, in the King's shaft vertically or inclined. This allows us to gather maximum info from the direction of the void. Each film package carries a bubble level, or an electronic equivalent, and a way to record its state. This way, the spatial orientation of each film will be known in the future. We deposit several films in each shaft. The carrying capacity is small, so it may take a few trips to place all films. The tourist traffic is not affected, so we can expose the films for a long time for more accurate results. When the exposure period is over, we retrieve the films, analyze the data, and find the best point of access to the void. If we're lucky, we may find a spot just above 1 meter from the void, like the closest spot between the Queen's shaft and the Grand Gallery. Once the best point is known, we proceed to the access stage. The equipment for this stage consists of 3 parts. The main robot, a small detachable device we'll discuss next, and support gear, such as air and water pumps, electric supply, and monitoring. If the best access point is in the Queen's shaft, the support gear can be set up in the Queen's chamber. If the best point is in the King's shaft, some of the support gear can be placed in the side space excavated by Caviglia, away from the tourists. Within the shafts, our operations are launched from what we call the main robot. Its function will be described later. It may pull a small wire cage trailer behind it to orderly store heavier cables. We access the void by drilling, but the drilling work isn't done by the main robot. Instead, it's done by a short, narrow, tethered drilling device deployed from the robot within the shaft. We'll call this unit the mole. Ideally, it would be not thicker than 1 inch, about the size of a glue stick. Of course, the smallest feasible size can only be found by real-world prototyping. The mole will drill through limestone on its own, its direction remotely controlled. Here's the proposed design. Obviously, real-world prototyping would force changes. Metal parts are in medium gray, other colors are plastics. The drill bit at the front is for use on limestone. It's driven by a metal flex shaft in the center. This shaft is within a protective, flexible metal coil. Such flexible transmission of rotary motion over distance is known from tools like Dremel. The flex shaft and other conduits are held within a flexible plastic sleeve in dark green. Just behind the drill bit, wrapped around the sleeve, are 3 separate inflatable bladders, shown clear or in light blue. They're made of thin, stretchable plastic, possibly with tougher coating for wear resistance. Each bladder can be inflated individually. This cross-section through the sleeve shows all air ducts. These 2 serve the back and middle bladders. In a short stretch behind the bladders, they're outside the sleeve, with some slack, able to move independently. We'll soon explain why. The mole travels within the limestone in a channel it carves out itself, so it has to move forward on its own. This is done with peristaltic motion. It happens when segments of a tubular body alternately bulge and contract to move forward. The best-known examples are intestines transporting food and an earthworm. In our mole's case, it's done by the bladders. Here's a schematic of the whole system. There's no need to grasp all this, it's just to document the current design. The mole is shown within a round, narrow channel carved in stone, in beige. The support gear outside the shaft sends air, water, and power to the main robot in the shaft, via tubing and a cable. Miniature valves on the main robot, like these, set the flow to individual bladders. Here's how the mole propels itself. The bigger locking bladder in the back is covered with dense rough points, similar to a sandpaper. As this bladder inflates, these points bite into the surrounding stone, locking the bladder in its current position. Then the middle bladder inflates. Its expanding accordion shape pushes against this washer. The washer, via this rigidly fastened metal tube, transfers the pressure to this ball bearing, and thus to the drill bit. The drilling phase begins. Crucially, The back and the middle bladders are mechanically isolated from the central sleeve and the drill bit, since they rest on metal tubes slightly larger than the sleeve inside. This, in conjunction with some slack on their air supply tubes, lets the sleeve and the drill bit slide with respect to the two back bladders. Prolonged drilling in stone often works better with water. If needed, water flows to the drill bit via this small upward outlet. Driven by a suction pump, this downward inlet then removes the slurry. Once the drill bit has progressed some predetermined distance, the drill phase stops. We inflate the front bladder, wedging it against the stone. We deflate the back locking bladder, releasing its grip on the stone. A vacuum pump removes the air from the middle bladder. It contracts and pulls the back bladder forward via the connecting washer. The mole has now advanced some predetermined distance. The back bladder inflates and the cycle repeats. Obviously, using a flex shaft, a relatively large bit, and working in cycles is far less efficient than a hand-operated, rigid drill. But the mole can move through stone in places inaccessible to humans. Steering the mole is plausible, though obviously in very gentle arcs, not tight turns. The front bladder can be divided into 4 sections. Before the drilling phase, any section can be inflated, exerting pressure on the drill bit in the opposite direction. Space in the pyramid's shafts is very tight. Drilling flex shafts don't bend into tight angles. First, we'll need a starter hole, about as wide and long as the mole. This is done by a separate drill, perpendicular to the channel. First, the legs at the back of this drill extend and brace against the opposite wall. An air bladder located in between inflates, exerting pressure on the drill. The drill's axle is made of telescopic concentric cylinders, interfaced with a central drive shaft, so the drill can reach some distance into the wall. Because of the very tight space, we may have to drill a shallower adjacent hole to make inserting the mole easier. The mole is inserted at an angle, while the robot gently pulls forward. The mole can now drill into stone by itself. The mole has no onboard camera. There's not enough space, and wet drilling is too dirty for a camera to be of any use. In a way, our mole operates like a real blind mole. So how will we know when we hit an empty space? Through the rate of pressure increase in the middle bladder. If the drill bit pushes against stone, the pressure increases rapidly. If there's empty space ahead, the pressure increases slowly. If we encounter empty space, the mole withdraws. An endoscopic camera unwinds off a spool into the hole to inspect it. By the way, we'll need dust guards to shield the wheel axles and the camera from the dust produced by drilling. Pressure sensors are on the main robot, near the valves. 1 or 2 may be aboard the mole, but only if space allows. Distance marks on the sleeve would show the absolute depth of the drilled hole. The sleeve may also carry bend sensors, every dozen inches or so. This would let us estimate the shape of the drilled channel and where the mole currently is in 3D space. This robot performs complex mechanical tasks. To properly monitor them, we'll need cameras high up and in the center, as opposed to just showing what's ahead in the shaft. The mole may encounter a few possible hurdles, but the R&D needed to deal with them, and equipping the robot accordingly is best left until they actually occur in real life. A few examples. The mole can encounter an unusually wide gap between 2 stones. Possible solution: the mole can bridge the gap with an expandable tube, like an artery stent. Another possible hurdle: the distance to the closest point in the void may be more than several feet. This would call for a longer, more robust drive shaft. The main robot may experience too much vibration during drilling. If so, we'll need more bracing mechanisms like this one. When the drill bit dulls, we withdraw the main robot and replace the bit outside the shaft. Carrying spare bits and replacing them in the shaft is possible, but it would probably overload the design. The method proposed here meets our initial goals. No drilling in areas visible to the public or areas sensitive to structural integrity, and minimizing the impact on tourist traffic. 3 robots had already visited the shafts in the past with no bad effects. Similarly, small holes have already been drilled in the shafts. Again, nothing bad happened. We believe that the approach shown here would let us peek into the big void within our lifetime, with minimum risk.